Hello class, welcome to a discussion on introductory probability. This is chapter 14 in your book. We're going to look at randomness tied to more formal mathematical probability today. So, similar to use with simulations, we can identify the probability, that is the percent chance that an outcome takes place, by running lots of trials. Let's check out the probability that for each of two volunteers, each volunteer makes a shot in the black milk crate over the trash can with an empty Mountain Dew bottle. Well, blah blah blah, law of large numbers, etc., etc. Let's go to formal probability. Probabilities are always numbers between 0 and 1. That is to say that if you have the probability of acing your final in stats equal to 0, there is no way in heck that you are going to pass that final exam. If you have a probability of 1 that you're going to ace your final in stats, that means it is a certainty. There is no way it can't happen. Anything that is uncertain but can still happen falls between 0 and 1. For instance, the probability that you pass the final equal to 0.5 means you've got a coin flip chance of passing your final in stats. For any event A, we write the probability of A between 0 and 1 usually like this. Let's say the event A is how to write it? Let's write it like this. The event A is you smoking a cigarette after taking a test. So the probability that you smoke after taking a test might be equal to 0.8. That means that you've got an 80% chance of randomly smoking after taking a test. Obviously that's a little bit silly because it's not truly a random event. Your willpower, your decision making comes into play there. Okay, let's talk a little bit about sample space. So, suppose you ask Mr. Shelton to stay after school to help you with stats concepts. There are a few possible outcomes of such a trial. The trial in this case is what happens after school when you show up to the room. Do I show up? Do I not show up? Or am I late? That is to say, am I on time? Am I late? Or am I a no-show? Those are the only possibilities here. And that represents those three events, those three red underlined events, represent the sample space of possibilities in this trial where I'm showing up or not showing up to help you after school. S, capital S, generally is our abbreviation for sample space. So we can use a Venn diagram to represent the sample space. We have really three figures here. The box represents the sample space. Those are all the outcomes from the trial, with me perhaps showing up, me perhaps not showing up, or me perhaps being late. So let's color code this a little bit. This red circle here will be the event that I am on time. Okay, it has some associated probability. Perhaps the probability is 0.15. So there's our first event, on time. The second event in the sample space would be that I am late to give you homework help. So we have late here in blue. The probability of that event might be something like I don't know, let's say it's ridiculously high, 0.80. So there's an 80% chance that I show up late to give you homework help. And then finally, in green, we have the final event that I am a no-show. I do not show up at all. I totally space. I've got something else going on, and I pull the absent-minded self that I tend to be on you. So no-show, 0.05. Notice that those three separate probabilities, 0.05, 0.15, and 0.80, added up, 0.05, 0.15, and 0.80 is equal to 1. That is to say, the sample space constitutes all possible outcomes in this trial. I cannot be anything other than late, a no-show, or on time. That's the only three possibilities that make any sense at all. Okay, moving on. Let's assign probabilities the four outcomes we discussed last slide. That should be 3, not 4. Okay, so this is basically doing what I just did. Suppose the probability that I'm on time is 0.55. Suppose the probability that I am late is 0.15, so a lot lower than I first gave you. And suppose the probability that I am a no-show is 0.30. If you are asked what is the probability that I'm not on time, there are two different calculations you can get to find that probability. The first is to say, well, what was I getting at with this question? Probability that you're not on time. If you didn't know the green probability, if you only knew the red probability, the probability that I was on time was 0.55, and the blue probability, the probability that I'm a no-show is 0.30, here's one way to calculate the probability that I would be not on time or late. That you could do that by saying, well, the sample space, all possible outcomes, are 100%, or one of the different ways that this trial can take place. We're going to subtract, because being on time and being a no-show you cannot be in those two events categories and also be late. So we're going to subtract off here. 1 minus 0.55 minus 0.30 should give us the probability of this third event, the probability that you're late. So the probability that you're late is equal to 0.15, which is what we already found. Alternatively, what is the alternative? What was I getting at here? That's the only way to do that. The directions don't quite make sense. Okay, so there's a complement rule based upon that. Okay, suppose instead you wanted to determine the probability that you are on time, or this capital U represents or in probability. The probability that you are on time or that you are late, though not you, rather me as the teacher, and showing up to help you after school. How could you go about this? Well, think back to the idea of the sample space. In this case, we've got three things going on. I am either late, a no-show, or I am on time. Okay, so the probability that I am on time or late, I can calculate one of two ways here. Because these three separate events, late, on time, and no-show, are all called disjoint or mutually exclusive. That is to say, I as a teacher cannot be in any of those two categories at the same time. I can only be in one. Because of that, we can use this idea of the complement. We can say, well, the probability that I'm on time or late is equal to 1 minus the third event in this case. The third event not covered by the probability we're trying to find here, right here. That would be 1 minus no-show, which was like 0.15, something like that. So the probability that you're on time or late would be equal to 0.85 in this first case. But there's a second way to calculate that. Because being on time and being late are again disjoint, mutually exclusive events, they have no overlap between between their outcomes. I can't be on time and late at the same time. We can just take the separate probabilities of on time and add that to the probability of being late to get the same thing. If the probability of being on time was 0.50 and the probability of being late is 0.35, that would mean the probability of being on time or late is again just 0.85. So you can either use the complement rule or add the probabilities directly on time and late because they're disjoint events. Okay, new example here. Suppose that upon entering Mr. Shelton's classroom, I am in one of two positions in the room. Suppose that 35% of the time I'm sitting at the chair and 65% of the time I'm standing in front of the class as you enter the classroom. So, first thing to ask ourselves is, do we have, with probabilities of 0.35 and 0.65, do we have disjoint events here? Yeah, we have covered the sample space. 100% of the outcomes in terms of where I am when you enter the classroom are included in this problem. So the probability that I'm at the chair, 0.35 again, probability that I'm at the front, 0.65, and let's work with that. Suppose you observe my position in the classroom on 2 consecutive days. How could you find the probability that I'm at the chair, and so that capital U represents or, the upside down capital U is and. What's the probability that I'm at the chair and at the front? That is to say, at the chair on the first day and at the front. Usually when we use this upside down U sign, that represents probabilities for when we're finding where we care about successive trials. That is to say, one flip and then a second flip of a coin, or one entrance into the classroom observing where Mr. Shelton is, and then a second entrance into the classroom observing where Mr. Shelton is. Something like that. Okay, so to find this probability, I think it's easiest to do that with a binary tree. So, as you enter the classroom on the first day, this over here, this little stem represents the entrance into the classroom, and then from that you've got 2 branches representing the outcomes for that trial. I am either at my chair or I am at the front. Okay? And we said that the probability of me being at the chair was 0.35. The probability of me being at the front was 0.65 on that first day. Okay, so simple enough. In this column, if you added those 2 probabilities, you get 1. So we covered the sample space. All the outcomes for this first trial of you entering the classroom and observing where Mr. Shelton is have been covered. Well, that's the first day covered. We want the second day as well. On the second day, one of 2 things happens for each of those first outcomes that has already transpired. Either I am at my chair, or I am at the front. I am at my chair, or I am at the front. Okay. Now, because, and this we can assume this fairly, because me being at the chair one day does not affect whether or not I'm at the chair or the front the next day. To find the probability that I'm at the chair this first day and there at the second day, I just take 0.35 and multiply that by 0.35. So this is 0.35 times, let's do that with a parentheses, 0.35, like so. Probability that I'm at the chair, then at the front would be 0.35 because I've been at the chair the first day, and then times 0.65 for the second day. Okay, so we're moving right along. Probability that I'm at the front the first day, 0.65. Probability that I would be at the chair, the front and then at the chair, 0.65 times 0.35, like so. Probability at front then front would be 0.65 times 0.65. So let's check out what happens here when I do this. 0.35 squared gives us 0.35 squared is 0.1225. 0.35 times 0.65 is equal to 0.2275. 0.65 times 0.35, same as what we had in the line above, 0.2275, and 0.65 squared is 0.4225. Again, we have covered all the possibilities in this new sample space. Over here in the first day, the two events that could happen were either that Mr. Shelton was at the chair or that I was at the front of the classroom, and those probabilities were relatively large. Notice how big they are compared to probability that I'm at the chair the first day, chair the second day, 0.1225, chair then front, 0.2275, front then chair, 0.2275, and then front and front, 0.4225. But again, they cover all of the events of this new sample space of you observing where I am at in the classroom on 2 consecutive days. All right, let's check this out. Master Foods Company manufactures bags of peanut butter M&Ms. They report that they make 10% each brown and red candies and 20% each yellow, blue, and orange. The rest of the candies are green. If you pick a peanut butter M&M at random, what is the probability that it is green? Well, because we're not given the probability of a green in the setup of the problem, we're going to have to use the idea of a complement here and consider whether or not these events are disjoint. That is to say, when we pick an M&M from the bag, can you have simultaneously in any assortment of outcomes here a brown, red, yellow, blue, and orange mixed together, or all those separate event outcomes? When you pick an M&M, are you only drawing one of those 5 different items? And of course, yes, that's true. So to get the probability of a green M&M, you look at 100% of the sample space and you simply subtract off the probabilities of the other events that we don't care about, the rest of the sample space. So that would be minus 0.10 plus 0.10 plus 0.20 plus 0.20 plus 0.20, the other 5 outcomes in the draw of an M&M from the bag. So the probability that we draw one green M&M is equal to, in this case, it looks like 0.20. Yeah, 0.20. Okay, so second question here. What is the probability that when you pick a peanut butter M&M at random, what is the probability that it is a primary color, red, yellow, or blue? Well, thankfully, because we just talked about the drawing of an M&M giving us disjoint outcomes. You can't have brown and red. You can't have yellow and blue occur at the same time. We're just going to say the probability of a red or this capital U sign, the probability of a yellow, or this capital U sign, the probability of a blue, is equal to the sums of those individual probabilities. The probability that we would draw one yellow plus the probability that we would draw one red. I did that backwards. Hopefully you see what is going on here. Plus the probability that I would draw one blue, which is equal to yellow 0.20, red, where's red? 0.10, and blue 0.20. So that is 0.50. There's a 50% chance, there's a coin flips chance that you would draw a primary color from the bag. Okay, finally, what's the probability that you draw an M&M that isn't orange in one draw of the bag? Again, just use the idea of the complement. So the probability that we do not draw an orange is simply solved by saying, well, that has to be 100% of the outcomes minus the probability that we draw an orange. Another way to go about this problem would be to say, okay, the probability that we do not draw an orange would be equal to the sum of the probabilities that we draw a brown, a red, a yellow, or a blue. So that would mean adding up 4 different probabilities. But that's not as easy as just saying, let's look at 100% of the sample space and subtract off the probability that we draw an orange, which is 1 minus 0.20. So probability we do not draw an orange is 0.80. And that is that. You guys are doing awesome. Okay, if you pick 4 M&Ms in a row, what's the probability that they are all blue? So our sample space has changed a little bit. Instead of drawing 1 M&M, we now have 4 separate trials. And with that, I need to stop the video and see how this looks on YouTube.